imagine we have a conductive plate in here, an insulator, and the p-type as the bottom plate. So two conductors with an insulator between them is what we defined previously as a capacitor. And if we connect a voltage in the top plate with respect to the bottom plate, as we talked before, the capacitor would be charged and the amount of charges on each one of these plates would be equal to C, which is the capacitance of the capacitor, times the voltage between the two plates. So if we apply this positive voltage in the way which is shown, then obviously we expect to have an electric field in the direction that is shown. We know that the majority carriers in the p-type are holes, so this electric field would cause the holes to go down. Soon on the surface it would be depleted from the holes, and we would say a depletion region has been created. If we increase the positive voltage here, then we know electrons would move in the opposite direction of the field, and electrons are the minority carriers in the p-type. So electrons would come up and would go on the surface. You would have electrons in here. Now, if we apply a positive voltage on one side with respect to the other side, then those electrons would obviously move to the positive side of the battery, and therefore we would have a current. This is the idea behind the creation of transistors. A transistor using this idea has been implemented in this way, that obviously we have the p-type as the substrate. Then we have the gate, a conductive plate, and we have the insulator between them. This is the insulator. Now we have two n-types that we call them source and drain. So as you look, we have three terminals: gate, source, and drain. Using the gate, using the voltage that we apply to the gate with respect to the p-type, to the substrate, we would create a channel in which electrons would reside on the near the surface in here. And if then we apply a positive voltage to the drain with respect to the source, as we explained before, then these electrons would move in the opposite direction of the electric field towards the drain, and therefore would have a current in the opposite direction. So as you see, this transistor is like two things. First, it is like an electronically controllable capacitor that by applying voltage to the gate with respect to the substrate, we could control the number of charges that would go on the surface. Second, after we have charges on the channel near the surface, we have electrons near the surface, then by applying a positive voltage to drain with respect to source, we could direct them, meaning now we have a resistor in the channel that electrons would move from source to drain. So what this is saying is that transistor is like a capacitor and a resistor. Using the voltage applied to the gate, we control the charges on the capacitor. Using the voltage applied to the drain with respect to source, we would direct its velocity, because you know velocity has a direct relation with the electric field. Therefore, we would create a current. Now, we want to extract, even though this the extraction of the I of the current of this transistor might be out of the scope of this course, but I wanted to show you so that you know there is no abstraction that we haven't talked about before. You have all the data that you need to extract the current and all the characteristics of this transistor, that how you could work with them. In fact, a transistor could work both as a switch in the digital world and as an amplifier in the analog world. And I explain a bit what I mean by that. So we know that the charges on the capacitor, we said, is equal to CV. We also know that the current that these charges, I guess, would contribute to would be equal to Q times V, in which Q is the, well, this Q is the total charge this Q would be the charge per unit length. Why? Because charge per unit length would have the unit of coulomb per meter, and voltage, the voltage that the charges, the electrons would get while undergoing the electric field, would be equal to its unit to meter per second, and therefore the result would be coulomb per second, which is the unit of the current. So our goal is to understand how much charges would collect or would gather in the channel, and then from then on, by putting that in this equation, by applying positive voltage to the drain, we would be able to calculate the current. So imagine, well, we want to calculate C. We show C as by multiplying it by A and dividing it by A. What I mean is that we show C as A times C divided by A. We call this C divided by A, which is capacitance per unit area, as C of oxide. And A would be the dimension of the plate, which its length, the length of the channel obviously would be, because this is one of the plates, right? The length of the gate would be obviously one of the plates, which almost is the same length with the channel that we have. So W times L times C of oxide would be the capacitance C. Let me actually increase this and change my color so you could better see that. So this would be the overall C, WL C oxide. Now we have to calculate for V. V is the voltage applied to the gate with respect to the substrate. Now this voltage, we said as we apply the voltage, we wouldn't instantly have charges in the channel, meaning every bit of this voltage wouldn't be spent to create the charges. Some of it should create the channel, because we said this channel would be created out of electrons, which are the minority carriers in the p-type, while the majority carriers are holes. So we first need this field, this voltage first needs to push down the holes. Therefore, we say the amount of voltage which is used to create the channel, which almost is that the surface should be as n-type as the substrate is p-type. Now, I don't want to go in more detail about this, but let's say this. Some of the voltage that we applied between the gate and the substrate would be spent to create a channel. This value is called V of threshold, meaning the voltage applied to the gate with respect to the substrate would be V of gate minus V of threshold would be spent to create a channel minus the voltage that we apply to the, well, actually we calculate with respect to the bottom plate, obviously. But what I want to say is this. You see, we have a capacitor whose upper plate is the gate, what we refer to as the gate. The insulator is between them, and the lower plate is obviously from source to drain. So our goal, obviously the voltage would be the voltage applied to gate with respect to the bottom plate. Right now, imagine that both the drain and also the source are connected to the ground, and we have applied a positive voltage to the ground, to the gate with respect to the substrate, or substrate is connected to the ground as well. So in this way, the Q would be C times V, like always. Well, C, we said it is WL times C of oxide, and the voltage would be V of gate minus V of threshold. Now we show everything with respect to source. Since source is connected to the ground, so this would be V of gate source minus V of threshold. This would be the overall charge on the plate when both drain and source are connected to the ground. In other words, if we want to show our capacitor in this way, and we show the channel as the amount of charges that would gather on the surface, we would have a channel like that when both the drain and the source are connected to the ground, and gate would be connected to a positive voltage, and this P would be connected to the ground as well. Now imagine that we connect the drain to a positive voltage. Now we connect the drain to a positive voltage. Now, what is the charges on the plate? Well, the bottom plate still would have the voltage of V minus V of threshold, because V of threshold is spent to create the channel. What about the bottom plate? Well, the bottom plate could have any voltage from 0 to L, which we show it as V of X. Well, the bounds of this V of X at the source is 0 and at the drain is V of drain, whatever that value is. So we say the overall Q is obviously C times V, and C we calculated as WL C oxide V of gate source minus V of threshold, which is the voltage applied to the gate minus the voltage that is being spent to create a channel, minus V of X, whatever that V of X is. Well, now to calculate the charge per unit length, we just divide it by L, and the result would be WC oxide V of gate source minus V of threshold minus V of X, whatever that is. Well, I is obviously equal to this value, well, charge per unit length times speed. And we know, well, let me actually show it, charge per unit length times speed. And speed we know is equal to mu n times E, and E is the derivation with respect to the X. Now, this E would have a minus here, minus d of V over d of X, but we know that current is defined as the opposite direction of the electrons in the direction of holes, so that minus, that negative sign would cancel in this negative sign, and the overall result for the I would be positive. Now, you might get a bit confused in what I said, but everything that we have defined here, all abstractions have been talked about in the previous lectures. So I think if you only look at the fundamentals, that how a capacitor is charged, how many charges would go on the place of the capacitor, and how we defined current, you wouldn't need any other thing. So let us just substitute everything that we got here. Q would be WL C oxide V of gate source minus V of threshold minus V of X, and V would obviously be mu of n d of V with respect to d of X. We multiply both sides by d of X and then we integrate. On one end we have I d of X, on the other end we obviously have W mu of n C oxide V of gate source minus V of threshold minus V of X with respect to the voltage, and the bounds in here is 0 to L and in here is 0 to V of drain source, that we explained why we are integrating through the length of the channel. If we calculate this integral, you see one part is this, well, obviously W mu of n C oxide would come out of the integral, so on one side we have V of gate source minus V of threshold times V from 0 to V of drain source, and on the other side we have minus the V of X again from 0, V of 2 divided by 2, obviously the integral of V with respect to V is V2 over 2 with respect to V of drain source. If you calculate this integral, obviously this side would be IL. If we calculate both sides and just replace V of drain source to V, then the overall result would be mu of n C oxide WL, then we would have V of gate source minus V of threshold, V of drain source minus V of drain source squared over 2. Now, what does this equation tell us? Well, it's so simple. If you look, it is saying if this term, just imagine that V of drain source squared divided by 2 is so much smaller than V of gate source minus V of threshold times V of drain source. Obviously, one of the V of drain sources would be cancelled out, so we have V of drain source. If it is so much smaller than 2 times V of gate source minus V of threshold, then we could ignore this term. And what we would end up with would be that we'd say I is equal to mu of n C oxide W over L, and this term, which is V of gate source minus V of threshold times V of drain source, and this is I of drain. Now, look at the terminals of the transistors that we show it in this way. This is gate, this is drain, and this is source. And obviously, V of drain source is connected between the source and drain. This is saying if the relation between V of drain source and I of D is like this, meaning we have V of drain source divided by I of D is equal to 1 divided by mu of n C oxide WL V of gate source minus V of threshold. And this is the Ohm's law. You remember we said V is equal to Ri. You see, we have a resistor between two nodes, and the value of this resistor is given by this equation. If the voltage applied to the gate, what we defined as gate, is smaller than V of threshold, or just imagine V of threshold, then this value would be 1 divided by 0, or just infinity, means that we would have an open circuit, meaning that the value of the resistor is just too big that we could just estimate it with an open circuit. If this V of gate source, on the other hand, is bigger than V of threshold, then we could just estimate it with a short circuit. You see, a lot of times, a lot of these kind of things that I'm talking about are defined actually in the range, like for any chip in any data sheet that we talked about. We usually see in the data sheet that there are concepts like V of IH, V of OH, V of IL, V of OL, that they just explain well, how a switch would work, in what ranges a switch would act as an open circuit or a short circuit. But as I said, I don't really want to confuse you too much. What I want to talk about is that we just found out that in a transistor, in this way, when we apply a V of drain source, which its value is much bigger than V of gate source minus V of threshold, then it acts as a switch. This switch works in this way, that the switch would be controlled by the voltage applied to the gate. If the voltage that we apply to the gate is smaller than V of threshold, then the transistor would act as an open circuit. And if this voltage is bigger than the V of threshold, then it would be a short circuit, and therefore it would act as a switch. Well, we have two kinds of MOSFETs. One of them, we call it an NMOS, which we talked about, gate drain source, and the other is called PMOS. And this would be again gate, source, and drain. Well, right now we want to define the lowest voltage and the highest voltage of a circuit as 0 and 1. But as I said, it is really in a range. It's not exactly specified as the lowest voltage and the highest voltage. We say for the NMOS, if V of gate, as you see in here, V of gate source is 0, meaning the lowest voltage of the circuit, obviously the switch, the transistor, should be off, meaning it would act as an open circuit. If we apply the highest voltage, or 1, we say V of gate source bigger than V of threshold, then the transistor would act as a short circuit. For the PMOS, it's the opposite. Applying a 0 would make the transistor to go on acting as a short circuit. Applying 1 to it, it would act as an open circuit. These are everything that you need to understand for the transistor. In fact, transistor works in another way. When the value of V of drain source exceeds the V of gate source minus V of threshold, which in that way the transistor would be used as an amplifier and you would enter the analog form. But in here, as long as the V of drain source, and we defined all the terminals based on the structure of the MOSFET, what gate is, what source is, what drain is, but everything goes back to the fundamentals. I really don't want you to get confused, and I feel like maybe I haven't explained this lecture that good, but my goal was that I could use as few abstractions as I can, or only the abstractions that we have defined in this course. But the important thing is the structure that we defined would act as a switch based on some conditions. This switch is controlled by the voltage that we apply to one of the terminals called gate. We have one MOSFET transistor which acts as a switch with two different conditions. In the next lecture, you would see how these conditions would help us in creating different logic gates.